Thank you very much, and I want to really thank the organizers. So this has been a really fantastic conference. It seems like a reunion of old friends. Somehow, like there's so many different, I think most of us here, our work is sort of in dialogue with Benson, who has been a great influence on certainly me, and I think a lot of people here. So it's just been lots of fun. It's like I've been in graduate school again. So today, I want to talk about something that's maybe a little bit different than some of the things that people have been talking about, but I should first say this is joint with Church and Farb. Though you might expect that there's something to do with representation stability, but I swear to God that this has nothing to do with that. So I promise. So instead, I want to say something about number theory. So we haven't really done a lot of number theory in this talk, though a lot of it's been lurking in the background. So let O be a number ring. So, and I apologize, I'm not very good with whiteboard, so my handwriting might be even worse than usual. So by a number ring, for example, Z is a perfectly good example of maybe the Gaussian integers, Z adjoin I, maybe say Z adjoin the square root of 2, something like that. And so what I want to talk about is the cohomology of SLN with entries in this number ring. So say SLNZ. What can we say about its cohomology? So this is the meeting ground of many subjects from automorphic forms, geometry, and so on and so forth. So what's the, and by the way, like how would a geometer think about this? Well, SLNO, this is a lattice in a semi-simple Lie group G. So for instance, SLNZ is a lattice in SLNR. These semi-simple Lie groups act on these beautiful spaces called symmetric spaces. So this is a very familiar thing. Say SL2R, this acts on the hyperbolic plane. And more generally, if you have any semi-simple Lie group, it acts on something like the hyperbolic plane. And so therefore, these groups, these lattices, they act on those properly discontinuously. So their cohomology is the cohomology of the quotient. OK, so what can we say about these? The sort of beginning of the subject is a theorem of Borel from 1974. So what did he do? So he calculated the cohomology, so HK of SLNO with Q coefficients for n much larger than k. So this is what's called the stable cohomology. So this has been, this is sort of a, there's been a lot of talk about stable cohomology in this conference. This is actually one of the rare situations where it was calculated before it was proven to like the proof of its stabilization actually is a calculation. So what is I'm not going to tell you the answer. The answer basically just depends on the number of real and complex embeddings of O. OK, so, and this is obviously a big story. There's actually many open questions you can ask about this. So for instance, the precise stable range is not known. So it follows from work of Ruth Charney and Heinrich van der Kollen that there's a stable range of slope 2, but there probably should be a stable range of slope 1. Integral calculations, that's a big mystery for the stable cohomology. Also, Borel's proof used Hodge theory. It was really an analytic proof. And it'd be very interesting to do something more algebraic topology. I think the algebraic topologists don't know how to calculate this. But I'm going to tear myself away from that and do something that is almost the precise opposite of this stable cohomology. So what do I mean by that? So let's let nu, that right there is the virtual, you can ignore that word, cohomological dimension. Of SLNO. So the cohomological dimension is the top degree in which there can exist some, in this case, because the word virtual was there to ignore torsion issues systematically. So it's the top degree in which there can exist some rational cohomology, maybe with some local coefficient system. So this is finite. I told you earlier that these things they have a k pi 1, which is this locally symmetric space. So it's a manifold, and therefore it has finite cohomological dimension. And in fact, a precise formula is known, and this was calculated by Borel and Serre in 1973. I don't want to give you the precise answer. Again, it depends on the number of real and complex embeddings. But for example, the virtual cohomological dimension of SL in Z is equal to n choose 2. OK, so this is the top dimension in which something can happen. And this is where n is, this is sort of the opposite situation of the stable cohomology. So I think I'm going to lead off actually with two theorems. So this is what these two theorems are what this talk is about. So theorem 1 says that there's actually a lot of stuff happening in this top dimension. It says that this dimension, the dimension of this top dimensional cohomology group of SLNO, almost everything in this talk will have two coefficients. That's greater than or equal to some quantity. What is that? So it's this, CL of O. That right there is what's called the class number. I'll say more about that right now. I mean, not right now. I'll say more about that in about 5 minutes. And you just think of the class number of O. That's some measure of the arithmetic, of how complicated the arithmetic is. You take that minus 1 and raise that to the n minus first power. So this says that in this top degree, there's a huge amount of cohomology. And in fact, it's very, very unstable. It grows exponentially as long as the arithmetic is complicated. Okay, so this is the first result. And by the way, another observation, I said that the stable cohomology really doesn't know much about the ring of integers. It really only knows the number of real and complex embeddings. This depends in a very delicate way on the arithmetic. So this is somehow the unstable cohomology is much more arithmetic than the unstable cohomology is more arithmetic than the stable cohomology. So when you first see this theorem, your first thought is, how sharp is this? So for instance, when the class number is 1, so Z is an example of something with class number 1, this says that it's greater than or equal to 0, which is maybe not the most interesting theorem. So you might say, is it because we're stupid, or is it because there's nothing else to find? And the answer is that in many cases, at least, there's nothing else to find. So that's the other theorem I want to talk about. So. No. Speak for yourself, Ben. Oh. So theorem 2 says the following. And I have to put some hypotheses here, unfortunately. So assume, well, as I said, assume the class number is 1, and also assume that either O is Euclidean, which is actually a strengthening of class number. It says there's a Euclidean algorithm. That certainly means you have unique factorization. So this means you have class number 1, CLI. I forgot how to spell as I was saying that. So, or assume that O is it has a real embedding. So you can embed it inside the real number. So for instance, Z join the square root of 2. That would work for that. And so the conclusion then is that this top dimensional cohomology group, H nu of SL in O with Q coefficients is 0. So let me make a few remarks about this theorem. So the first is that in the Euclidean case, this was already known. So this is due to Lee and Charba in 1976 for O Euclidean. Though our proof, even in the Euclidean case, our proof is very different from theirs, of a very different flavor. So that's the first thing. And the other remark, which I won't even write down, you might say, well, what about this other condition, outside the Euclidean case, the totally real condition? So how necessary is that? And the answer is that you need to have some other assumption there. You can show, it follows from computer calculations done by people like Karen Volkman, that this is sometimes false in the imaginary quadratic case. You look at non-Euclidean rings of integers, which are imaginary quadratic and have class number 1, and some of those have some non-zero cohomology in the top degree. If you assume the generalized Riemann hypothesis, then aside from imaginary quadratic things where there's only finitely many units, class number 1 is the same as Euclidean. So assuming the largest machine gun I know, not just the Riemann hypothesis, but in fact the GRH, which you can sort of give a sharpening of this. But these are the conditions I need for the theorem. And I'll maybe, I think since I'm going to save, the parts of the proof I'll discuss won't really tell you where this comes in. So I'll just say in words, the reason this totally real assumption comes in is because we actually need the congruent subgroup property for these. And it turns out this is a theorem of Bass, Milner, and Sayre that SLNO has the congruent subgroup property, which is a classification of all finite index subgroups if and only if O has a real embedding. So anyway, that's how that assumption comes in. I'm going to say a lot more about how this class number 1 assumption comes in. So these are the two theorems I want to discuss in this talk. So the next thing I want to discuss, so I said that this CL of O is the class number, and this is not an audience of number theorists. This is an audience, there's some representation theorists, there's some topologists, there's, a wide range of people. Many people have not maybe, heard about the class number years ago in graduate school, but haven't thought about it. So how should we think about this class number as a topologist, as a geometer? So that's what I want to say next. So class number. So I'm going to give you a definition of it, which is maybe the wrong definition from an arithmetic point of view, but the right definition for this talk. So the first is, let me just give you the sort of first property you should know, is that so CL of O is equal to 1. That's true if and only if O is a unique factorization domain. So you can factor any number uniquely into a product of prime numbers up to units. So, and that's true in this case if and only if O is a PID. These are not, for general rings, these aren't the same, but for rings of integers, they are. Okay, so larger class number says, if your class number is bigger than 1, that says that unique factorization fails, and the bigger it is, the more it fails. That's how you should think about it. But how do you, what does the actual number mean? So here's a fact. And you should take this fact as the definition for this talk. So the class number, CL of O, this right here is the number of orbits of the action of SL2O on, well, so K here is the field of fractions of O. So for instance, if O was Z, K would be Q. And well, SL2O, it acts on K squared, but what we're really interested in is the action on the set of lines in K squared. So the number of orbits of the action of SL2O on the set of lines inside K squared, that is the class number. And that's how you should think about it for the purposes of this talk. But let me motivate that. What does this have to do with unique factorization? So, K, oh yeah, that's right. So K, I said it in words, but I didn't write it down. So K, that's the field of fractions of O. Okay? So Q, for instance, if O was Z. So I'm going to prove a special case of this, which will maybe give you a hint on what this has to do with unique factorization. So here's the special case. Is where O is equal to Z. So Z has unique factorization, so the number of orbits should be 1. The class number should be 1. And how do we do that? Well, consider some point, which I'll write in homogeneous coordinates, A comma B, inside the projectivization, in this case of Q squared. So I want to show that I can take any line, like so this is the line spanned by A comma B. So A and B are, they're well defined up to scaling by Q, by non-zero elements of Q. And so I want to say I can take, using SL2Z, I can take any two of these to each other. And so I'll take 1, 0 to it. So what do I do? Well, I said I can scale these. So what I do is I clear denominators. So without loss of generality, first I clear denominators and make A and B both integers. And then I cancel all common factors and I assume that they're relatively prime. Okay? And so then what can I do? Well, when you see the words relatively prime, you should have some Pavlovian response. It says that there exists some numbers C and D, integers, such that AC plus BD is equal to 1. And what does that imply? That implies that this vector AB, that right there is equal to, well, we could take AB and then we put C and minus D times 1, 0. That right there, that's an element of SL2Z. Check. That's what we wanted to show, right? So the SL2Z acts transitively on the set of lines in Q squared. And now, what does this have to do with unique factorization? Well, there's what it has to do with unique factorization right there. So I had to assume these things were relatively prime. And so the failure of this proof measures how much unique factorization fails. So in any case, though, as I said, you should take this as the definition for, I'm going to prove something in a few minutes, and then we'll use this fact as the definition. So, and I guess I should give you one example for something that's got non-trivial class number. So I'll give you the easiest example, the one you usually do when you teach a first-year graduate course. So the class number of z adjoining the square root of -5, that's 2. Okay, and so this should reflect some failure of unique factorization. And what is that? Well, 6. Well, 6 is, I think it's 2 times 3. But it's also 1 plus the square root of -5 times 1 minus the square root of -5. And it's not too hard to check that every number I just wrote down is prime. And these are genuinely different factorizations into products of prime numbers. Okay, so that's the class number. And so with this fact, you now have a complete statement of these two theorems. Okay, good. So the next thing I want to do is I want to discuss a special case of theorem 1. I want to explain sort of what geometrically is going on here. And I'm going to explain it in the case for n equals 2, because for n equals 2, it turns out that this is actually a very classical theorem. It's new for the case n greater than or equal to 3. Let me erase this. Always, if you're on YouTube, you should go look for, there's a video of Denis Roux erasing a board at MIT when he's teaching calculus. And it's amazing. It takes him 3 swipes. Like he spins it up and goes, and it's gone. You know, it's the greatest thing I've ever seen in my life. Unfortunately, I can't do it. So, yeah. Special case of theorem 1. So what is the special case I want to do? So well, I'm going to do n equals 2, and I'm also going to do O is the integers in Q adjoining the square root of -d. So d should be a positive square free number. Okay? And so now let's set r equal to the class number. It can take many different values here. And so what we want is for the dimension of H. Well, what's the cohomological dimension of SL2O in this case? It turns out it's 2. And I'll explain why in a second. So of SL2O with Q coefficients, I want that to be greater than or equal to R minus 1. I can't write today. OK. So how do we do this? How do we understand this group geometrically? So the first thing to observe is, so SL2O, that right there is a subgroup of SL2C. In fact, it's a discrete subgroup. And what's more interesting is that it's discrete and the quotient is finite volume. So this is a lattice inside SL2C. Now, what is SL2C? That right there, the geometers in the audience know that that is more or less the isometry group of hyperbolic 3 space. I guess I really should have a P there, but I'm going to ignore that. OK. So what I can do then is I can form the space X, which is hyperbolic 3 space, modulo this group SL2O. So this is a hyperbolic 3 manifold right here. And this is, ignoring torsion issues, a k pi 1 for this group. And so I want to produce some cohomology, some elements of H2 inside this 3 manifold. Nota bene, this 3 manifold, you know, its cohomological dimension, well, you might think, well, it should be 3 because it's a 3 manifold, but it's not compact. And I'll explain its non-compactness in a second. And because it's a non-compact 3 manifold, its cohomological dimension is strictly less than 3. And it's not, and I'll produce some elements of H2 in a second, so it's not 1. OK, so that's why the cohomological dimension is 2. But now, how do we understand this 3 manifold? So what's the first thing you learn about hyperbolic 3 manifolds? You learn what's called Margulis's lemma, which tells you the structure of what's going on in infinity at the cusps. So what does this look like? So it looks like it's got some cusps right there. And so these cusps, what they look like, so it's got some topology in the middle. And these cusps, so they look like a torus cross R. So it's a torus heading out to infinity and sort of scaling down so you have finite volume. OK, so let's give these cusps names. So I'll call. That's a picture of X, right? Yeah. This is X. That's right. So, and of course it's a 3-manifold. So that's, but I don't know how to draw. You know, I'm like Benson. I don't know how to draw any manifold other than a surface. So so that's a 2 torus. So let's give these cusps names. So that's C1. Well, actually, before I do that, I should tell you how many there are. And so now comes the basic connection between the topology of this 3-manifold and the arithmetic. So let's remember, class number is the number of orbits of SO2O in the set of lines in K squared. I'm going to erase this now, but I'll recall it in 2 seconds. Okay, so I suppose 2 seconds have passed. I'll recall it in a minute or so. It's an audience of mathematicians, so I should not say anything that's literally false. So I'm going to lose that. So let me set this over here. So here is the basic fact. So R here, remember R is the class number, so that's equal to the number of cusps. Okay? So why is the number of cusps equal to the class number? So what are the cusps? Well, the cusps, let's go back to the structure of Kleinian groups. These are in bijection with the set of conjugacy classes of parabolic subgroups. I'll tell you what those are in a second. Actually, first I'll destroy the carpet of SL2O. So what is a parabolic subgroup? So a parabolic subgroup, that is the stabilizer of a line. So in this case, it would be, so this line side C squared. So for example, the canonical example would be, so the subgroup 1 star 0, 1. But you don't care about, if the stabilizer really is the identity group, then you don't care about it. So we might as well just forget C there and replace that with K. Because if you choose a line that's not really a line coming from K squared, then the stabilizer will be the trivial group. So that's not very interesting. And by the way, you can see that these are tori from this picture right here. So this star here is some element of O. O as just an abelian group is Z squared, right? Because elements are, well, more or less, they're A plus B times the square root of negative D. There might be a 1/2 in there for reasons I want to ignore. So this is really a Z squared. The subgroup is a finite index subgroup of Z squared. So it actually is Z squared, and that's why it's the fundamental group of a torus. Okay, so these are stabilizers of lines. That's the parabolic subgroups. That right there, well, just rephrase that. Those are the orbits of the action of SL2O on the set of lines inside K squared. Well, that's the class number, right? So so check. Okay. So we've got so the cusps, the number of cusps is in bijection with with these orbits, and so the number is the same as the class number. Okay. And this, by the way, works, of course, for n equals 2, no matter what O is, you're going to get some structure like this. The number of cusps will be the class number. So, okay, so let's give these cusps names. So there's C1, C2, C3, and C4. Okay, in this case, 4 would be R. So let's let gamma ij, that right there is a line connecting. So Ci and Cj. So for instance, in this picture,
are you thinking of, when you say cusp, are you thinking of like just cut it off in one of the tori? Because otherwise, where's it going to connect?
It's going off to infinity.
Oh, okay.
So it's heading out to infinity like this. Okay? So that is gamma 1, 4 right there. So it's heading off to infinity out each cusp. It might do something in the middle, but we're going to ignore that. Okay, so these aren't unique, but just choose one for each pair of cusps. Okay, so what I claim is that this guy right here, I set down the wrong Merker. So this right here is dual to an element gamma ij inside, well, I claim it's dual to something inside H2 of X. Where is that? Well, what should an element of H2 do? It should eat a surface and defecate out a number, right? Or spit out a number. So in this case, how do we do such a thing? Well, you take a surface inside your 3-manifold, and it's going to we wiggle things a little bit, and it's going to intersect this infinite line in a finite number of places, and we just count those intersections with signs. So it's an algebraic intersection number. Here we really only care about compact surfaces, so we can ignore sort of what's going on in infinity. So this is dual to an element of H2, and by the way, it's not dual to 0, because, for instance, this torus right here intersects it exactly once, and so it has something that it's dual to. Okay, so here for every pair of cusps, we've constructed an element of H2. Now, they're not linearly independent, of course, not necessarily, but certainly if you look at, so gamma 1, 2, gamma 1, 3, all the way up through gamma 1r, those are linearly independent. For instance, you can see that you can find things that are dual to them that are the different cusps, the C2, the torus in C2, the torus in C3, and so on. So check. That's exactly, there's r minus 1 of those. That's how much H2 we wanted to produce. So this is the general picture for n equals 2. So I don't want to stop now. So let's, what's going on? By the way, what time am I supposed to stop? I forgot the 3:25. Fantastic. So the, what'd you say? Yeah. Inches 2, where's inches? Isn't that what the cohomological dimension is? No, that's for z. Yeah. So in any case, though, we see that somehow there's we can get some cohomology by studying what's going on in infinity inside these manifolds. Okay. So for higher n, there's still cusps like this. There's still cusps at infinity, but there's a real problem, and that's that those cusps overlap in complicated ways. And so therefore, to produce cohomology for higher n, we need to do a more profound study of the geometry of these cusps. And so that's what we do. So I want to say something about that, because that also will play some role in what's going on in theorem 2, this vanishing theorem I stated. So I now want to discuss the geometry at infinity. So the analog for SL2, SLNO for NEO, there's going to be some version of hyperbolic 3 space. And I want to say what's the sort of analog of what's going on in infinity here. So what's going on in infinity in this case, you can see it's got something to do with lines inside k squared. And so, if you're looking, if this 2 was replaced by a 3, you wouldn't just have lines in k squared, you'd also have planes. And that's what's controlling the geometry at infinity, it turns out. So let me discuss that next. So let me make some definitions. So the Teeps Building is a combinatorial object that encodes all these lines and planes and stuff like that. So Teeps Building so I'll denote that by Tn, in this case of k. This is the simplicial complex with p cells. P in this case isn't prime. It's just a convenient letter because I've used k for too many things already. So they're flags. So 0 is strictly contained in V0. Is strictly contained all the way up through V sub p, which itself is strictly contained inside k to the n. So for instance, it has vertices for any proper non-zero subspace of k to the n. So lines, for instance. If n were 2, it would just be a discrete set of points, one for each line. So we already saw that's sort of what's going on in infinity in the n equals 2 case. And more generally, it's an insight of Borel and Serre that what's going on in infinity in the locally symmetric spaces, or the associated SLNO, is modeled combinatorially by this building, this Tn of k. Okay, so therefore, we want to understand the topology of this building. And so that's governed by what's called the Solomon-Teeps theorem. And maybe I look, that was written down about 1968. And so what does it say? Well, the first thing is, what's the dimension of this space? Well, the maximal flag is going to go from v0 all the way up to v n minus 1, right? And so therefore, the dimension is n minus 2. Okay, so what it says is that there is only one degree of interest in cohomology. So it says that Tn of k so is homotopy equivalent to a wedge of n minus 2 spheres. Okay, so it's, for instance, if n equals, this is consonant, for n equals 2, it's just a discrete set of points. Well, that's a collection of zero spheres, right? So it's a wedge of a bunch of zero spheres. So what this says is that there is, but there is some interesting cohomology here in degree n minus 2. So this is what's called the Steinberg module. You should think of this. This is the cohomology at infinity. So we'll denote this Stn of k. That right there is this cohomology, or I'm going to say homology, in degree n minus 2 of this Teeps building. And then to avoid tensoring things with q later on, I'm just going to put a q there. So this right here is, by the way, there's an action of SL in k that acts on the Steinberg module because it acts on the building, and by just permuting these subspaces around. So we get an action on homology here. Okay, so I said you should think of this as something going on in infinity here. So if this space were compact, it would have Poincare duality, right? There'd be a duality between the top dimensional cohomology and the bottom dimensional homology. So this is not compact. It's a manifold with cusps. So it's got something going on in infinity. And so therefore, we should expect some analog of Poincare-Lefschetz duality for manifolds of boundary or manifolds that are not compact. You look at something compactly supported. So but we want to do something group theoretic. So that was done by Borel and Serre. So this is called Borel-Serre duality. And so what does that say? It says that if we look at, remember, nu is the cohomological dimension. So h nu minus I of SLNO with q coefficients, that right there is isomorphic. In fact, it's naturally isomorphic to the dual of hi of SLNO. Well, that's what we'd have if we had a compact manifold. This would be Poincare duality. Here, because it's Poincare-Lefschetz duality, there should be some contribution from a boundary, right? Well, in this case, the boundary lies at infinity. And I told you this Teeps building is encoding what's going on at infinity. And so therefore, it should what you put here is the Steinberg module, the cohomology at infinity, the cohomology of the boundary. That's sort of the analog of doing things rel boundary in the group theoretic case. Okay. So we have this duality between h nu minus I and hi, but we have to twist by this Steinberg module. So this is another instance of twisted cohomology being important. What's a special case? We only care about one special case. We care about what's happening in the cohomological dimension. So a special case says that h nu of SLNO with q coefficients, that right there is isomorphic to h0 of SL in O with coefficients in the Steinberg module. That this has a special, the h0 of a group acting on some space, that is what's called the co-invariance. So I'm going to write this here, Stn of k, and you kill off the action of SL in O. So remark. So if M is a G module, so it's a module with some action of a group G, so M sub G is by definition M modulo, and we kill off little m, we want that to be equal to G of little m for all M inside M and G inside G. So we're taking M and we're killing off the G action. So this is what H0 of a group acting on some vector space is. Okay, that's great. So this is the thing that we're interested in. So we have to understand, in this case, to prove, say that this thing vanishes in some cases, we have to understand this action. So it turns out that the Solomon-Teeps theorem says a lot more than I've told you. It doesn't just say it's homotopically equivalent to a wedge of spheres. It tells you what the spheres are. So that's what I want to discuss next. So this is what are called apartments. So it's a building, and a building is made out of apartments, and those, even worse, are made out of chambers. But, the French, as you can tell, they have a great sense of humor. So, okay, that wasn't even funny. So let's let L be a frame in K to the n. What do I mean by a frame? That right there is a set L1 up through Ln, where these are lines with K to the n, a direct sum L1 plus all the way up through Ln. Okay, so associated to every frame, I'm going to construct a sphere in this Teeps building. Okay, and that sphere is called an apartment. So A sub L, that's the apartment. So of L and n minus 2 sphere. So what is the apartment? This is best done by example. So for n equals 2, well, then what do we have? We have lines L1 and L2. And hell, look, there's a zero sphere inside our apartment. Okay, so I don't really have any good jokes. That's the best you're going to get out of me. So that's a zero sphere, but maybe that's not the most enlightening special case. Let's look at n equals 3. What happens there? There we have L1, L2, and L3. Well, let's connect them by edges. Well, those actually are not edges in our complex. We'll subdivide, though. We'll stick L1 plus L3 right there, L2 plus L3 right there, and L1 plus L2 right there. And lo and behold, we have a circle inside our building, right? Because L1 is contained inside L1 plus L2, et cetera.
When you say plus, you don't mean adding the 1? You mean the direct sum?
Yeah, I mean the span, yeah. Yeah, this is like an internal direct. I'm putting a plus because it's an internal direct sum. So okay, so we have our spheres, and so what does Solomon-Teeps say? They say that this Steinberg module, the h n minus 2, this is spanned by the apartments. Okay? So these spheres give you everything. Now, they're not linearly independent, but they do give you all the spheres inside our complex. And so observe that S L in K, well, that acts transitively on the apartments. But, and this means, you first might think this is great, we can understand this action, but we don't want SL in K, we want SL in O. And so SL in O does not. And in fact, that action encodes a lot of interesting arithmetic. For instance, we saw earlier that the action of SL2O on the set of lines, the number of orbits is the class number. So you can see this action, and those are apartments. Those lines, any pair of them give you an apartment. So this action really has some interesting arithmetic properties. And so the way we understand this action is we want to find a smaller set of apartments where we can understand it, but which span everything. So that's the last minute or so of my talk. So here's a definition and a theorem, and then I'm going to stop. So definition. So L is integral if, well, so I want to be an integral frame. So this is a direct sum decomposition of K to the n. I really want a direct sum decomposition of O to the n. And so it's integral if O to the n is equal to, well, L1 intersect O to the n plus all the way up through Ln intersect O to the n. So it's best to see a non-example. So let's say that O is equal to Z. And so then if we take the set, so take the span of the vector 1, 2, and the span of the vector 1, 0. So these 1, 2, and 1, 0, I put a q there because I'm taking a line. So these are linearly independent, so they span q squared, but they don't span z squared, right? The determinant of them is 2, not 1. So this is non-integral. These are the things we're fighting against. Okay, so theorem 3, this is sort of the key to theorem 2, is that let's assume, and this is due to us, so CFP. So what's the conditions there? Well, it's the same conditions as theorem 2. CL of O is equal to 1, and either O is Euclidean or O has a real embedding. So then the conclusion is that this Steinberg module, Stn of k, is spanned by integral apartments. So let me make some remarks. So the first thing right here is this is due to Ash-Rudolph in 1979 when O is Euclidean, though with, again, a very different proof than ours. When it has a real embedding, it's definitely new. And I should also say it's false when for CL of O greater than 1. It's false in every case in that situation. The relevance for that is that these intersections, well, these intersections are projective O modules, and when the class number is 1, then they're actually, the class number tells you the number of projective O modules, so they're trivial in that case. But if the class number is greater than 1, they might be non-trivial projective modules, and that causes trouble in the proof. So, and you can prove actually it fails. You can, by a sort of counting argument. And so SLNO, assuming the class number is 1, acts transitively on these integral apartments. In fact, it acts very transitively. You can permute the vertices inside them and therefore change the orientation in the coinvariance that says that each of them is equal to its negative, and so therefore the coinvariants are 0, and that proves theorem 2. And that's where I'll stop.
Other questions? Sort of, how often when you have a number field to adjoin something is SL2 of that something discrete subgroup of SL2C?
Very rarely. So let me give you an example to show you what's going on in that case. So, I'm going to give you a slightly different example than what you asked for, but you'll see the general picture. Let's look at SL2 of Z adjoin the square root of D. Assume that D is such that this is the ring of integers. What's this a lattice in? You might think this is a lattice inside SL2R. That's not right, because it's not even a discrete subgroup of R, right? Z adjoins the square root of D is not discrete. And so what you do is you embed this inside SL2R across SL2R, where you just use the embedding that takes some matrix, it takes A plus BI to the pair A plus BI and A minus BI. And that makes it discrete, and it turns out that makes it a lattice. So, oh yeah, B times the square root of D. I'm sorry, you're right. Square root of D. I'm acting by the Galois group here. Yeah, when D is -1, that would work. But then this would be C and not R. So, so you see what you do in general is you take, you look at the number of real embeddings, you stick it inside of SL and R for those cases, and for each pair of complex conjugate embeddings, you stick inside of SL and C, you take that big product in this way. And that's how you stick this thing inside a semi-simple Lie group discretely. Does that answer your question? Yeah.
And like for this case, you can just see, like for any SL2s, you can just see that, like you're saying, Z adjoining the square root of D, like it's non-discrete at all.
Yeah.
But it is discrete.
It is discrete in R squared. Yeah. The fact this is discrete is a fun exercise. Like if this number, if pair of numbers both approach 0, well, if A plus B root D and A minus B root D approach 0, then their sum does. So therefore, 2A approaches 0. Since they're integers, it means A eventually better be 0. And similarly, their difference tells you that B eventually has to be an integer. More general, the real miracle is that this is finite covolume. So that's a much more difficult result. In this case, in this level of generality, it goes back to Siegel. So, did I see a? Okay. I thought I saw a question over here. Yes.
Actually give you like a basis.
Right. Yeah.
Can you say how big the spanning set is in this case?
I mean, so the problem is, so that basis is things that are not, they're not integral. So they're very, you might think they are because it's the upper triangular matrices, right? But you have to clear denominator. So the upper triangular part, those are definitely rational numbers. And so, the understanding of the action on that basis is really complicated. I don't know, I don't know how to. Yeah, it's not preserved by the group action. And somehow, so for instance, I actually do not know how to write down a set of integral apartments that span, that are a form of basis. They all together they span, but there's many linear dependencies among them. So it's a theorem of, I guess it was proven by Baikovsky, Church and Farb, and I. Well, I guess Church, we have a new proof of it, which gives you the relations between these things, at least for O is equal to Z, but they're complicated. So. I don't know how to prove that part of the Solomon-Teeps theorem in this case. It is probably not a reasonable answer. Yes?
I mean, you guys get a sharp lower bound. Is there some way of using either Solomon-Teeps or somewhere else to get an upper bound on this?
So what you'd have to do here is you'd have to hope to get an upper bound. You'd have to find, so you have to find the relations between these integral apartments, right? That's what you'd have to understand. So for Z, such a thing is known. You can sort of get an upper bound, but it's actually pretty hard to calculate. For Z, the answer is 0, but that's not so interesting. But in general, I don't know what the relations are. Our proof for that is special. It doesn't even work for other Euclidean domains. It's very special to Z. So I think that it's very hard to do. I think I don't know how to do it. So any other questions?
Going with